Today is our first video about the Microblaze. It's a set of tutorials that I created for you guys. Some of you asked to talk just with the Microblaze, which is actually a soft core, which means is a whole processor that is going to be placed in your FPGA through HDL. So it's not like the Zinc. It's not like a sub-core inside your FPGA. It's really using it's a processor that uses the logic part of your FPGA. And this has some advantages and disadvantages as well. I'm going to switch on the board to explain how the Microblaze works, what are the main features, what are the limitations, and we're going to the lab after that to show a simple hello world. Probably going to use as well an Axi Timer just to show how to use a little bit of more cool stuff there. Okay guys, see you guys in the board. So, Microblaze. First of all, Microblaze is a 32-bit soft core, which means is a whole processor that is going to be placed inside your FPGA using the logic fabric. Okay, it's not like the Zinc that you have an ARM processor that is really part of the hardware. It's really going to be using the gates in your FPGA. Okay, what are the main features of Microblaze? It has a floating point unit, a memory management unit, sorry, a memory protecting unit, which means you can use Linux in the Microblaze. It can have up to 16 kilobytes of cache. Okay, it has support for Axi 4 and Axi Stream ports, and in the case of an RTX 7, can go up to 200 MHz. Okay. This is one of the limitations. For instance, in the case of the Zinc, that you can go up to 1 GHz. If you're using only the logic fabric in your FPGA, this is more or less the maximum that you can get with a normal FPGA using Microblaze. Okay? A good advantage is that you can put like 2 or 3 Microblazes in the same FPGA, so it's really parallel if you would like to think of that. Okay, here is more or less how you connect the Microblaze in your Vivado. Okay, actually you start with the memory interface generator that is going to connect with your DDR. Okay, then you add your Microblaze. Okay, the Microblaze has an internal memory. Okay, where the code will start is actually implemented in the VRAM. Okay. As seen in previous videos, the VRAM is a fast internal memory that is placed in your FPGA. Okay, it has a debug module where you use to set breakpoints. Sometimes you want to use also the UART through the JTAG. Okay, but it's low. Actually, I prefer to add an IP core for UART, which has a connection with the USB. Okay, and an important point that we should observe is that the Microblaze has actually 3, actually there is a debug port as well, but those here are really important. Normally you use the instruction cache and the data cache connected to an interconnect that is going to map only cores that actually deal with memory. For instance, the memory interface generator or the DMA. Okay, it's not a good idea to use the instruction and data cache channels to put, for instance, an UART or Axi Timer. Sometimes this can make your program crash. Okay, actually you use the data peripheral channel. Okay, to map UART, Axi Timers, block run controllers and stuff like this. And doing this, actually you decouple. You're not going to allow some of these guys mess with your coding memory. Okay, now I'm going to present a little bit in which board we are going to use, and then switch to the lab. Okay, guys. This is the board that we are going to use on these Microblaze tutorials, and some of the HLS videos as well, especially when I'm going to talk about the Axi Masters. Okay. So this is the RTX Avinet RTX 50 demo board. Okay, it has 2 Ethernet ports, 1 port for programming through USB for the JTAG, one port here for the UART through USB as well. It has 1, 2, 3, 4, 5, 6 PMODs connectors. Okay, here is actually when we want to use some GPIO. Okay, and it's a nice board. We're going to play a little bit with this board for the Microblaze. And okay, so let's switch to the lab, and we're going to use how to work with this guy. Okay.
Hi guys. So we're going to start our tutorial by creating a Microblaze simple hello world. Okay, let's call it hello world. Okay, the board that we're going to use is the Arctic 7 evaluation board from Avnet. And okay, so let's just wait the project to initialize, and I'll create a block design. Okay, if you come here to boards, and by the way, this just happened because I have installed the board support package in Vivado, and we start just by dragging the DDR memory. That's it. Okay. So, for instance, by running the connection automation here. Okay. And now we add our Microblaze. We're going to start with there are two versions, the Microblaze and the Microblaze MCS, which is kind of a microcontroller version of the Microblaze. Sorry, no microchip, microcontroller version of Microblaze. Okay, but we're going to stick with the common Microblaze, and we're going to connect our Microblaze with the UI clock port. Here we can configure the amount of memory that you're going to have in the cache as well. Okay, and let's just press OK, and the clock automation will do all the job. Well, in this case here, if you click twice here in the Microblaze debug module, there is an option that you can add a JTAG UART. Okay, but in our case we want to use the UART that we have in the Arctic 7 board anyway. Okay, so we probably come here, memories, miscellaneous, USB UART. Okay, we just drag and drop here, and cool, and we run. Let's first just connect the UART, and I'll show another detail. So let me just do a zoom out here, maybe this. Okay, so here is our interface with the DDR. Oh, sorry, not here. Where is the MIG? Here, exactly. Okay, so actually we need to connect our DDR controller with our Microblaze. Okay, and we just do this by run connection automation, and we run here MIG, and this stands for data cache and instruction cache. Okay. Up to now, we're going to continue to add in more stuff in the Microblaze, but this is enough for our hello world. Okay, we validate just to verify if everything's fine. One point that is missing now is that we need to, for instance, we need to define which pin we're going to use the sys clock. The sys reset, I believe that is already done. So for this, we're going to save the block design. Okay, just in the address editor here, we can see where our DDR actually start will be here, but we're going to see that in the future. So we just run. We are not interested now to generate the bit stream directly. We're going to run the synthesis, And I forgot one point. We need to come here to sources, and we need to create an HDL wrapper, which is going to create an HDL file that's actually going to instantiate this block diagram. Okay, otherwise you are not able to synthesize nothing. So run synthesis, and after this is done, we're going to assign the unmapped pins to our FPGA pins. Okay. Okay, now that the synthesis is done, we're going to open the synthesized design, and the idea is that now we're going to check the device I/O window, and we're going to check if there is any pins that has not been assigned yet. Okay, so at this point we just drag and drop on the desired pin, and the constraint file will be automatically created. Okay, let's just wait the synthesized design to open. Okay, and then at this point here we can actually configure our pins. We just drag and drop on the position that we need. Okay, just some information. These pins here are clock specific pins. Okay, actually the other pins has already been set, and now it's just a matter to drag and drop the 6 clock pin in the right position. Okay, also we need to change the I/O standard. In this case is LVCMOS 33. Okay, for our clock, and the right position that we need to drag and drop our 6 clock. So on this AVNet board, the clock is located at the location N11, so we can just drag and here at the location N11 and drop, and we are good to go. If we save it, an automatic a constraint file will be created automatically. Okay, here we can see that the I/O standard and the pin of the 6 clock E signal has been fixed. Okay, guys. So well, now we just synthesize again. And after the synthesis is done, we generate the bit stream and verify if any error occurred, and if not, we are good to go. We're going to export the results to the Xilinx SDK and write a simple hello world program. Okay. Okay, guys. Now that the synthesis is done, this constraint file is already applied in our synthesis results. So in theory now we are good to go. We can click here and generate bit stream. Then the implementation and all the process in between, actually just the implementation, will be run. Okay, so generate bit stream. I'll pause here the video just to come back again when it's done. So the implementation is done. I will just open implemented design just to show you some information. It's nice to know more or less how much space you're losing in the course. I mean, you want to see, we are going to show more or less the FPGA itself and the resources used per IP core in the whole FPGA. Okay, so I'll just minimize a little bit to have a better view. Here is actually the timing summary. We're going to talk about this later when we actually want to fix timing issues. Basically, you don't want negative values here, but we're going to talk about this in the future. Okay, so now I'm going just to select and change the color of all the resources that are related to the Microblaze alone. And I put a different color, let's say blue. Now the MIGs, which is actually the memory controller. You see that these guys actually use a lot of resources. way more than our Microblaze itself. Let's select the UART, the interconnect, and let's put a different color, just yellow for instance. Okay, so actually this is more or less the blue part is the Microblaze and the stuff related to the Microblaze. The red part, the memory interface generator, which is our DDR controller, and in yellow, let's say the rest, the UART, the interconnect, and stuff like this. Okay, now let's open the hardware manager, and I will connect the Arctic 7 board here, and we're going to okay, before that, let's export the hardware to Xilinx SDK. Okay, and because sometimes you want to program your FPGA through Xilinx SDK, so it's good to export and have the latest bit stream there. Okay, now I will connect the board, and we jump to SDK and write some software. So now with the board connect, we come here, Auto Connect. We have here our FPGA. The system monitor is quite cool. If you double click, you can see, for instance, the temperature and the voltage being used by the internal core. Okay, sometimes this is useful because you write some program and you want to see how the temperature in your FPGA is changing and stuff like that. But let's program the device. And after this is done, we can come here and launch SDK, and the Xilinx SDK will open, and we are good to write our software. Okay. So guys, inside of the Xilinx SDK, here is some hardware information that is being generated through Vivado. Okay, here is our memory, our DDR. Here is actually the address of our local memory. Here is the address of our UART peripheral. Okay, so we come here to File, New, Application Project. Let's do, I don't know, Hello World App. We should choose C++, and we're going to create a new BSP. By the way, don't confuse this BSP with the BSP of the board. This is just the name that Xilinx SDK have for it. Cool. So the application is here. You actually it creates oh, sorry, some empty main file. Let's just include if you guys are short in space, there is an option. Instead of using printf, you can use the XIL printf, which is quite smaller. In other videos I'll show how to use. In the case of the Microblaze, this can make a difference. Okay, so before we compile, here this is the linker script. Here is where the stack size, the heap size, where actually your local memory will start, where actually your DDR memory will start as well. Okay, and let's continue. We come here now. If you just go here and run as and choose launcher on hardware, probably he will complain saying that you did not define your STDIO, which is the case here. So you come here, run as, run configuration, and here we choose. Actually, this depends on the board that you chose. Let me just jump back to Vivado because I actually don't remember the baud rate. Okay. So we apply and run. Cool. Our program is working, and our IP core is actually working there as well, the UART light. So let's play a little bit. Let's add, for instance, a timer there. So back in Vivado, let's add our timer, Axi Timer, and hopefully I will also make an error appear that is really funny, that you add the timer, but the timer is not detected as in Xilinx SDK, and I will show how to fix this issue. So actually just want one timer. Okay, now we run connection automation, and okay, attention that we are adding actually to the master peripheral, and as I explained, this is good because we don't want to have this changing your instruction address. Okay, if you come here to address editor, you see that in data we have the timer, the UART light and stuff like this, but for instruction only the MIG or the DMA or something like this in the case that you need. Okay, so let's save. We can validate as well to see if there is no problem, and I will just jump the process that we're going to actually generate this bit stream. Okay, and I'll switch to Xilinx SDK because I already have the board using this IP core. Okay guys, now in the Xilinx SDK, it's quite annoying, this bug. Actually, in the previous step we add an Axi Timer, and then we export the project and we bring to the Xilinx SDK. But by some reason, the timer header for the driver for the Axi Timer is not being detected. And how you solve this? You need actually to regenerate the BSP, and it's quite simple. You come here to BSP, click twice in the system.mss, you modify the BSP settings, and in drivers we choose the driver timer control. Okay, and it started the BSP regeneration. Okay, now if you come here, you see there is not an issue anymore. Sometimes it's marked there that you have the timer set, but the error continues anyway. So in this case, you set to none, regenerate, set to the timer, and regenerate again, and it will work. Okay. Now, actually here we just want to measure the printf time. Okay, and let's run the program and see how it goes. Cool. It takes 0.001 millisecond to print the hello world. Okay, so let's finish the day. This is enough for an introduction on Microblaze. And the next video, when I talk about the Axi Master, I'm actually going to use the Microblaze. Okay, so see you guys in the next video. Hope you guys enjoy it. Bye bye.